Until the 1960s, it was Venus, not Mars, that everyone assumed we would first colonize and terraform. As it turns out, they may have been correct after all. So today we will be following up our look at colonizing Mars by exploring the options for colonizing and terraforming Venus, and we will see that it is probably the best prospect for true terraforming inside this solar system. Until the 1960s, we thought it very likely it might be a paradise planet. It had clouds and was closer to the sun than us, but we didn't know until we got a better look that it was super hot and had a day longer than its year. That, indeed, will be the trickiest part to properly terraforming it, as we'll see later. We knew its mass was 82% of Earth's, and its surface gravity was 90% of Earth's, and again, since we could see clouds, we figured there was a chance it might be habitable or even inhabited. As observations improved, we found it wasn't a paradise, but a good deal closer to a very hot oven. Even the clouds are made of sulfuric acid. At the same time, we discovered it's quite possible that had not always been true. Indeed, Venus might have been a lot more Earth-like in the distant past, and maybe even hosted life. But while we can look at Mars and say maybe it once did too, and cross our fingers of finding fossil evidence of that, it's very unlikely any evidence would remain on Venus if it ever had life, as the surface has been periodically resurfaced by floods of lava. Venus has the most volcanoes of any planet in the solar system. So when we found out how extremely hot this planet was, most folks scratched colonizing Venus off the list. And yet, as we'll see, it's not only a decent colony location, but a great one for terraforming as well. When we left off last time in the Colonizing Mars episode, we followed a traveler who went to Mars and explored the options for colonizing it. That traveler spent several years there and has since decided to go home and return to Borman Station, our large space station above the moon. I mentioned then that the moon and Earth's orbit were decently settled already, but that besides Mars and a few asteroid mines, the only other manned mission in the solar system was a floating scientific outpost above Venus. And that mission has wrapped up and just been replaced by the first settlement floating in the clouds, and the ship that brought it there returned with the crew from the outpost. When we get back to Borman Station, that crew has also just arrived themselves, to much fanfare. We get to talking to one of the members and she happily recounts the basics. Venus has a very thick atmosphere, about 100 times that of Earth, in defiance of its very minimal magnetosphere and proximity to the sun, both of which should tend to result in losing your atmosphere. That atmosphere is almost all carbon dioxide, with just over 3% being nitrogen and only trace amounts of other gases. And yet, even though Earth's atmosphere is 78% nitrogen, Venus's atmosphere has more nitrogen than Earth's simply because it has so much more atmosphere. Down on the surface, the supercritical carbon dioxide forms a sea, having characteristics of both a liquid and a gas, which will be important for terraforming the planet. However, like any atmosphere, the higher up you get, the thinner it gets, and it cools down too. At about 50 to 55 kilometers up, the atmosphere is down to about normal Earth pressure and temperature. While pressure and temperature are now approximately that of Earth, the gas mix is still almost entirely carbon dioxide, which has a molecular weight of 44, so any gas with a lower molecular weight can act as a lifting gas like hydrogen and helium do on Earth. That means that hydrogen and helium, with a molecular weight of 2 and 4 respectively, work even better on Venus than on Earth. But it also means that even our normal oxygen-nitrogen air mix, with an average molecular weight of 29, would float a balloon on Venus. That's obviously advantageous, since it means a room full of air will float, assuming the room and its other contents aren't too heavy. But hydrogen and helium are still better. They are in dreadfully short supply on Venus though. However, the lack of oxygen in the air also means that hydrogen is a much safer lifting gas than on Earth, and you can get hydrogen, oxygen, and water out of the sulfuric acid that makes up the clouds. So while it is neat and handy that normal air is a lifting gas on Venus, you probably want the majority of your lifting done by hydrogen anyway. Up in the atmosphere, the lighting is a lot like on Earth, except that if you stay in the same spot, you will have a day-night cycle not of 24 hours, but 243 days. Since the day-night terminator creeps along at a fast walking pace even at the equator, you can opt to stay in perpetual sunlight if you want to, making it handy for solar power or growing plants to help recycle air and water, and extend food supplies. We tend to think of blimps needing to be very small and light, but you can make some large blimps, potentially some very large and sturdy ones with mass manufacture of graphene, and carbon for making graphene is hardly in short supply on Venus. You could potentially use that for making diamond-hard tethers anchoring you to the ground, possibly able to survive the super hot acidic hurricane below, or use them like harpoons with a winch to drag your sediment around like a big octopus. But we also have a superabundance of solar to power engines, and all that wind lets you consider using wings to provide lift, like a plane or a kite, not just buoyancy. Many normal restrictions get eased with enough energy and strong enough materials. So there are a lot of options for moving around up there in the clouds, and our companion on Borman Station is quite upbeat about the idea of building even larger habitats in the clouds of Venus, floating islands in the sky. However, we are fresh back from Mars, and the problems they were having there, so we ask her why you would want to do that. She's just spent a couple years with a research team that are very enthusiastic about Venus, and knows we just came from Mars, so she is a bit taken aback by the question. From her perspective, because we can is quite a sufficient motivation. But back on Mars, we were already seeing some of the problems that happen as a colony gets big enough that science and prestige are no longer good motivations for getting bigger. We were all for the Venus mission and even a permanent floating habitat there, but the notion of building thousands of giant floating cities seems harder to justify. We say as much, and she points out that it's no different than Martian domes. Indeed, those floating habitats are easier to construct and maintain in many respects. They can't just mine up rock to build more, but there's plenty of material down on the planet, and we can build mining robots to be controlled from the floating habitats that can handle the heat and pressure, and potentially deliver those goods by either going up a tether or popping compressed gas cartridges to fill balloons and float back up. Mars has the option to simply dome over the entire planet, with various sized domes connected together, a thing called a world house. Venus could do the same. This approach, known as Terraforming, could produce archipelagos of floating habitats around Venus, or even entire continents of space eventually. But as we saw on Mars, it's not too clear why you would do this at that scale. Sure, you can float cities on Venus, but they still have to be very thin and light to float, and you can just orbit the planet in more conventional rotating habitats instead, like the one you're on now. She points out that being low in the atmosphere protects you from meteors and some radiation, and that the orbital speed around Venus is not much lower than Earth, so the settlement can float right over a spot you are mining. We point out those orbital settlements can have very thick radiation shielding, which also helps against meteors, which we can also shoot down. But these floating habitats have to be ultra-light, so they've got the radiation concerns of early space travel when every kilogram on board a ship cost a fortune, so shielding had to be kept to a minimum. Same now for Venus. It has no magnetosphere of note, so its radiation protection comes from that super thick atmosphere, and the cloud habitats float over most of that. We can put our blimps in water storage over the settlement to add some shielding, but radiation remains a concern. We are not convinced about the practicality of this approach, but we still decide we have to see it for ourselves. Since they are sending the ship back to Venus with the second round of colonists for that first floating settlement, and we are already here at Borman Station and trained in space travel, we decide to put off returning to Earth and join the crew. When we went to Mars, it was already decently settled with several thousand colonists. Venus is less built up, just a few hundred colonists on that first floating settlement, Niobe, and a few dozen at their space station, Vulcan. It's a shorter trip than to Mars, as Venus is closer to Earth, but it's still long enough to get to know the other crew members. We regale them with tales of Mars, as we've seen things these people wouldn't believe. Standing atop the peak of Olympus Mons, hang gliding through the canyons in Valles Marineris, attack ships off the shoulder of Orion. Well, that last one didn't happen, but we tell them anyway, many an awesome sight. When we arrive at Vulcan Station in orbit around Venus, we see it as a different setup than with the space elevators from Thalys' station on Mars, or Earth's orbital ring. Venus hasn't got anything like the infrastructure for an orbital ring yet, and its gravity is too high for the space elevators we have at the Moon and Mars, lower than Earth but still too high. Vulcan Station uses a rotating skyhook design, or rotovator. It's a simple, small habitat at the center of a long tether that spins in a circle as the whole thing orbits the planet. While the whole system orbits Venus just a little slower than satellites around Earth, the tip of the tether spins backwards, cancelling out some of that velocity, making it easier for ships to enter or leave the thick atmosphere to or from the tether tip. We come in on a shuttle much like an airplane, and air brake down to land on a large floating runway. It's pretty neat landing on a runway that just floats in the clouds, and we park next to a wall designed to keep the wind off us as we exit wearing nothing but a simple acid-resistant suit and breathing mask. Clouds above, clouds below. We've stood on top of Olympus Mons, more than twice as high as the peak of Mount Everest, and right now we're more than twice as high as that. It is quite a sight and worth the trip. There's no ground to see below. It's like looking upside down at a hurricane. Once that awe passes and the ship is unpacked, we find ourselves confronted by the same concerns we expressed earlier though. What is the appeal to a major settlement here? We can see a lot of tourism. It's not that long of a trip and you can wander around outside without a heavy suit. While we are working our way to the main structure, we are nearly clipped by a colonist flying overhead, learning the ropes of hang gliding with just a simple air tank, mask, and thin acid-proof suit. Those clouds are pretty, but still made of sulfuric acid. The equipment at this settlement is a lot newer than the stuff on Mars, which was settled a couple decades before we first visited several years back, so it is a lot more automated here and folks have more free time. We remark on this to one of the first wave of settlers as we settle in at the Venusian Cafe, and he chuckles and says in the future the first wave will be entirely robotic, and the folks talking about colonizing Titan in a few years are planning to go entirely robots and cyborgs. None of that here though. Part of the appeal of Venus is how Earth-like it can be, he says. No need to be a cyborg or get tweaked genetically to live here. You need a breathing mask and an acid-proof skin suit when outside, for now, but that's it. No, Venus is ideal for terraforming. Down the road, of course. It will be monstrously expensive though, and Venus hasn't got much for trade. In fact, the thing it has an ample surplus of is carbon dioxide and nitrogen in the atmosphere, and energy for industrial processes. If Mars wants to terraform itself, it will need a lot of that nitrogen, and even if they just want to terraform the planet, they'll still need plenty. If not, well, all those rotating habitats being built around Earth need nitrogen too. And carbon might be abundant, but it's also something we always need a lot of. He envisions a huge floating mass driver launching tiny, thin-walled pods of nitrogen. And if Mars wants them for actual terraforming, they don't even need to land them. They can just machine gun them at the planet to explode on arrival and have the fragments of the pod burn up in the atmosphere. They can get the metal for the pods from down below. Of course, mining the surface, which is essentially under a super hot acid hurricane, is rather tricky, at least until they can terraform Venus properly. We're curious about that and ask how. After all, the clouds are fine, but down below it's still a hellish landscape around 462 Celsius or 863 Fahrenheit. He shrugs. What makes Venus hot is its proximity to the sun. There are other factors, greenhouse gases gone wild for instance, but if you shut off the heat pump from the sun, it will cool down. We raise an eyebrow at that. The sun does not come with an off switch, and moving planets around is quite outside our reach, for now anyway. But he reminds us that there is only empty space between the sun and Venus. Block the light, and you block the heat. every planet has Lagrange points, specifically an L1 Lagrange point in between that planet and the Sun. Normally, the closer to the Sun you are, the faster you orbit, so if we placed an object between us and the Sun, it would not stay there. We can simply place a shade there, or mirror, to reflect light away. It would not need to be very thick or massive, though if it is too thin or fragile, we won't be able to cope with the solar wind. If it is too thick though, we would have problems keeping it in place, since L1 points are only marginally stable. Thin ones can use the light hitting them to maneuver a bit, like a solar sail, so we don't need fuel. So these shades aren't exactly just a piece of foil. Your typical one might be as big as a football field when deployed, but not weigh much, and devote a fair portion of that weight to manipulating the sail, the electrons to figure out how much and when, and some solar panels and batteries to power both processes. Ideally, you want something very light and strong, like graphene made of carbon, so you can manufacture them back on the cloud cities of Venus, deploying them to the L1 point by the millions until you shade the entire planet. Venus's atmosphere is mostly carbon dioxide, and we could also remove it from the planet. Indeed, that might be the better option. But if we block the light, the atmosphere will begin to cool, and at the pressures on Venus, it will liquefy at about room temperature. So you'd lose the thick atmosphere in favor of seas of liquid carbon dioxide. And if we kept cooling it, the carbon dioxide would freeze and the surface would all be dry ice. If we wanted to, we could pave that over, remove enough of the solar shades to keep Venus at a comfortable Earth-like temperature, and introduce dirt and water. We have to interrupt our companion though. Certainly there's no shortage of potential dirt, but water is another story. There's a decent amount of water in Venus's thick atmosphere, and all that sulfuric acid can be disassociated into water and sulfur trioxide, but it isn't enough for real oceans. Venus's entire atmosphere is incredibly massive, about a third the mass of Earth's oceans, but only a small fraction of it is water or hydrogen we could use to make water. Plenty for people to drink and grow food with inside greenhouses, but not enough for a classic biosphere. For that, we need to come up with somewhere between 10 to 100 billion megatons of hydrogen. Our companion nods. Hydrogen is an issue. It is the most plentiful stuff in the universe, and the solar system too, but outside the sun itself, the only real supplies of hydrogen are the gas giants. The sun's solar wind is a good source of hydrogen. It blows out about 1 billion kilograms of hydrogen a second, a megaton. But again, we need 10 to 100 billion megatons. And 10 to 100 billion seconds is 3,000 to 30,000 years, and that's if we gathered it all up, and it goes out in every direction. We could bring in ices from further out, but that's a more precious commodity, and truth be told, we really only want the hydrogen, which is only about 1/10 of a water molecule's mass anyway, so easier to move. If we can get star lifting working, we could boil hydrogen off the sun. Indeed, we could use that trick to clear the atmosphere on Venus too, using solar mirrors instead of shades to heat the planet even more and evaporate the atmosphere away. Some folks have even been discussing how you could colonize the sun itself, and they could ship hydrogen to Venus or even just aim a diffuse beam of hydrogen at the planet. But he thinks such ideas are still a little too blue sky to be taken seriously. Better, he thinks, to bring hydrogen in from Jupiter or Saturn. That would be the trade item Venus wants to import, hydrogen, which is in plentiful supply even compared to their huge need for it. All of which sounds good. It's actually a little less ambitious than terraforming of Mars by bringing in nitrogen, since you need a lot more of it by mass than Venus needs in hydrogen, and you would end with an Earth-like planet, not a low-gravity one. Except for the day length issue. Again, Venus's day is longer than its year, so the sun is going to rise and stay there for months before setting for more months. We've got 3 possible approaches to this, he says. First, we can just ignore it, and adapt life there for that condition, same as the bioformers on Mars were thinking about adapting life to live on Mars or meet halfway in the middle. However, Venus is the only planet in the solar system we can realistically classically terraform, so half measures seem kind of wrong. He points out that we already will have solar shades to limit the amount of light getting to Venus, so it doesn't overheat, so we could go in for mirrors too. Mirrors on a 24-hour orbit around Venus could be arranged to block incoming sunlight on the sun side and bounce light down on the dark side, and done so as to simulate a normal 24-hour day. You could even make a decent fake sun that way. Lots of mirrors that bounce light to something about the same angular size in the sky as the sun, which bounces it down to Venus. That would look very natural even. All those mirrors and shades would help protect Venus from radiation too, though we probably still want to consider an artificial magnetosphere like was planned for Mars to hold the atmosphere in. We can't expect that to stick around on its own once we make it Earth-like. The other alternative is to go all in and actually adjust Venus's rotational speed to a 24-hour day, or maybe save some energy and let people sleep in longer with a 26-hour day. We have to raise an eyebrow at this though. From a physics perspective, it is certainly possible, but it takes a lot of energy. We would need to add over 10 to the 29th joules of rotational energy to Venus to do this. That's a lot of energy, and yet it also isn't, relatively speaking. We needed to ship those massive quantities of hydrogen to Venus to give it real oceans, and that is going to require fairly similar levels of energy too. It's in the same ballpark, shipping in an ocean versus spinning up a planet. While 10 to the 29th joules of energy seems enormous, and it is more than 1 billion times the amount of electricity 21st century Earth used each year, it's also only a few minutes of total energy output from the sun. Similarly, it is about 10,000 years worth of solar energy hitting Venus, much of which we want to block anyway, and if we can build a planet's worth of shades, we can build that much or more of solar panels too. It's tricky to convert that into rotational energy though. You can't just put a big rocket thruster on a planet, especially one you want to cool down. Even hitting it with energy beams, like spraying a large ball with a hose on one side to make it spin, is going to add a lot of heat too. In fact, that might work with hydrogen as well, a big beam of it coming in from the sun like a water jet, hitting one side of the planet and injecting hydrogen and spin at the same time. But if we are shipping in hydrogen from gas giants instead, each of those ships or pods is moving quite fast and carrying a lot of kinetic energy. And as mentioned, the amount needed for transport is in the same ballpark as rotational energy. So we just figure out how much hydrogen we want and how much rotational energy we need, and make sure each pod full of hydrogen arriving is moving at a speed to deliver that energy. Indeed, if that were too fast, we might go ahead and ship in ice instead of hydrogen, and let the extra mass carry the extra kinetic energy. We would kind of prefer slow because we want to keep that mass, not having a ton of it explode out into space and wander away, which is a big issue when just hitting planets with asteroids or comets. It would be tricky to get that process to work, aiming big chunks of ice or pods of hydrogen to impact Venus near the equator on its edge to impart the maximum spin. But it is doable, and gets you 2 birds with 1 stone. Indeed, possibly 3, since if Venus is spinning faster, it might have a strong enough magnetosphere not to need an artificial one. We also have the option of giving Venus a moon. You can use those as gravity tractors to move planets or impart spin too, and the outer planets have an abundant supply of them they're not using. Most of them have a surplus of hydrogen too, so you could move one in, again multiple birds with 1 stone. Of course, you could also take a lot of the excess carbon from Venus and make one, either a full moon or a thick shell full of hydrogen or some other filler material. Building planets, or even moons, sounds like a huge project, but so is terraforming in general. Such things would take thousands of years. You can only go as fast as the planet can get rid of the heat, but terraforming is always going to be a long game. They don't have to make any decisions on it yet, they're just a floating settlement of a few hundred folks. But those are their options. They can go the orbital colony route, the floating cities route, the paraterraforming route, where they shade the planet to cool it down and use orbital meals to produce a realistic day, or go big and start slowly spinning the planet up to a 24-hour day, where possible by using incoming shipments of hydrogen or water to impart much of that spin momentum. Again, they don't have to decide yet, but the floating colonies cannot survive the cool-down process when the atmosphere eventually liquefies. You would probably have to abandon them and retreat to orbital colonies, unless you could figure out a way to safely modify them to float in the air, then land on the carbon dioxide sea, then transition to being in enclosed habitats on the surface as you make the changeover to early terraforming. We expect that during cooling you get a ton of earthquakes and maybe volcanic activity while it snows dry ice, and you eventually have to pick a way to either export or permanently sequester all that carbon dioxide so you can warm the planet up to Earth-like temperature and atmosphere composition. There's plenty of solid things you can make out of carbon and oxygen, but they all take a lot of energy, and even when you have plenty to spare, you do have to worry about that releasing heat, even for endothermic processes. It is doable, but I tend to think that carbon in the form of graphene is going to be the preferred building material in the future, so Venus might export gigatons of that. So we have a lot of options for Venus, and as with Mars, we don't necessarily have to only do one. You could have many phases with different configurations, or with more than one option pursued simultaneously where they can be. But I think that Venus, as the only planet really suitable for total terraforming, is more likely to be terraformed, and all the way too. You'd always need some solar shades to keep the heat down, but heck, we might need those on Earth eventually, and you can make it so they are seemingly invisible, just cutting down on some of the light, and particularly from the frequencies like infrared we can't even see. You can even move a planet if you really want to, but that takes far more energy than even spinning it would. Colonizing, though, does not necessarily mean terraforming, as we saw with Mars, and we will see even more in the next episode of the series, Colonizing Titan. Next week, though, we are going to look at the extreme alternative to terraforming, where you just build your planets instead, and return to the megastructure series to look at ring worlds, giant orbital habitats so large they wrap around an entire star and provide 1,000,000 times the living area of Earth, first suggested by author Larry Niven in his classic sci-fi novel, Ringworld. Since, unsurprisingly, that is going to be our September book of the month, sponsored by Audible, and we'll be doing some spoilers, you might want to click the link in the video description to grab a copy of the audiobook before then, if you haven't already read it, though I will try to leave the story itself mostly unspoiled in our discussion of the megastructure itself. The week after that, we will be celebrating the 3rd anniversary of the channel, and the original Megastructures episode, along with the 100th episode on the channel, with Smug Aliens, and discuss some concepts like the Zoo hypothesis and the Star Trek Prime Directive. And we will finish up the month of September with a 2-part episode collaboration with John Michael Gaudier to look at uplifting, the exact opposite of the Prime Directive, where you visit planets without any technology and give it to them, along with possibly altering them to have the brains and physiology to use it. For alerts when those and other episodes come out, make sure to subscribe to the channel, and if you enjoyed this episode, hit the like button and share it with others. And share your thoughts with others down below in the comments section or the Facebook and Reddit groups Science and Futurism with Isaac Arthur. Until next time, thanks for watching and have a great week.